Good morning, everybody. I think it's time to start off our part two of our Futures Bright for in-bin grain drying webinar series. I'm Glenn Wilde with Top Grade Ag, and Top Grade Ag is a ag tech company, and we're focused on bringing in-bin drying into the mainstream, and to be a true competitor with conventional grain drying. The reason that we decided to put together this webinar series is historically ag salespeople have really paid very little technical, provided very little technical support when purchasing in-bin drying systems, and the rules of thumb, like the 1 horsepower per 1,000 bushels, and really the lack of addressing the real technical details has created basically an instance where in-bin drying just isn't given the respect it deserves. So over the next 3 weeks, we're going to break down the technical side of things. The first webinar really gave a nice outline as far as the in-bin drying in general, and some real good data on the economics, and showed how in-bin drying is by far the most lowest cost on-farm grain drying system when you take into account capital. And now here in part two, I'm going to look more in depth at the aeration fan selection and just the science of in-bin drying. So the first thing that I want to talk to is why do we dry grain? Historically, grain drying has been a reactive type of process, and it comes down to it's getting late and I'm running out of time. That's when the farmer decides to pull out his dryer if he has one, and ultimately it's I guess a fairly deeply embedded instinct that the farmer is hoping that Mother Nature cooperates and that we don't have to dry grain. Now, what Top Grade Ag is sort of trying to introduce is the concept of proactive grain drying. Now, I guess with this concept, it's the thought process where the quality window is small, take it early, and preserve the quality. And it is a case that farming is getting more and more technical. The windows for applying your herbicides, for applying your fungicides, they're very small, but the quality window is probably the smallest out there. And it just seems that for the most part, we hold our breath and hope that we don't get the dews and we don't get the showers. A second, I guess, slogan would be expand the go time harvest window by taking it early. By relying on a reactive drying strategy, you're almost always drying in October, November, and this really is the highest cost time to dry your grain. So by doing the proactive drying, you end up drying in August, September, and as hard as it is to go and take grain when it's slightly tough, it makes a whole lot of sense if you have a low-cost on-farm drying system. And that really is the key to opening up proactive drying, is to have a system that you rely on and that you can actually dry your commodity 3 to 4 points and do it for 8 cents a bushel. All of a sudden, it turns into a really efficient insurance policy. During webinar 1, we went through the 6 different components. And what I want to do today is I want to focus in on 2 of these components. The first one is your air. As we had discussed, air provides 2 purposes. One is it takes the water out of the bin, so it's a conveyor to get the water out of the bin, but it also is a pipeline to get your energy into the bin. Here's a typical grain bin, and ultimately you've got liquid water that's in your grain mass, and the trick here is, how do you get your water to move? How can you remove it out of your bin? The key to that is phase conversion. You have to add energy to convert that liquid water to a vapor, and it is very simple science, and it's very repeatable and consistent. Once you've converted that water to a vapor, you need to have enough airflow to transport that water out of your bin. And really that is, in a nutshell, the science of removing water from your bin. But what I like to do is I like to use an analogy. It's a bucket elevator analogy, which kind of brings in all the different components of your air. So the key with air is that the warmer the air, the higher the carrying capacity. So you can hold a lot more water in the air when you're at 30 degrees compared to when you're at 1 degree. So what that refers to is warm air is a big bucket in your bucket elevator. Now, how full is the bucket with water? That relates to your humidity. So if you have 100% humidity, your bucket is right full. If you have 20% humidity, your bucket is just barely full at all. So you've got two factors. One is how big your bucket is and how full it is. And these things make a huge impact on the effectiveness of your drying system. And then the last component of your bucket elevator is how fast is this thing turning? How many buckets per minute are you actually removing? And that really comes down to your airflow. The perfect analogy there is how many CFM per bushel you're moving. If you're moving 1 CFM per bushel versus a half a CFM per bushel, you're going to be removing twice the amount of water, and it really is a simple proportional relationship. So that sort of takes into account the actual water removal, but now how about the energy side of things? And there really are 3 scenarios for energy. We talked about this first scenario, no energy input. This is the instance when you've taken off your grain, it's nice and warm, a 30-degree day, you bin it, and you're maybe a point or a point and a half tough. So what you're gonna do is cool the grain. And in this instance, you have enough energy to vaporize your water, and all that's required is airflow. You've got a cold air coming in, and that cold air is equivalent to a small bucket, and so you're bringing a small amount of water into the bin because of this low carrying capacity. As the air moves through the warm grain, the bucket increases because the air takes that energy and it picks up that moisture, and as the air warms, the bucket gets larger, and ultimately the carrying capacity is increased. So you end up removing water, and this has been proven. Ron Palmer at Indian Head, this was his I guess realization, and it kind of created the whole idea that cooling grain is drying grain, and that is absolutely the truth, as long as you have enough energy in the grain mass. Now, if you don't have enough energy in the grain mass, and let's say you cool your grain and you still are a point tough, well, now you have to add some additional energy. And the second scenario is adding ambient air heat. So that is what you would consider natural air drying, so no supplemental heat. Now, when we're doing this process, again, we're gonna have to warm the grain. So we're gonna have to add energy to the grain, and we're gonna be bringing in warmer air. So when you're bringing warm air into the bin, you will 9 times out of 10 be bringing more water into the bin. And what is really tricky with natural air drying is the ratio of the amount of water you're bringing in compared to the amount of energy. Sometimes it isn't enhancing your drying. So sometimes you're bringing in more water than energy, but ultimately you're going to warm the grain, and as that air is cooled, because you are taking energy out of the ambient air and adding it to the grain, so the air temperature is dropping, your bucket is getting smaller, and in many instances, you're actually dropping water into the grain. So in this instance, often what you're going to be doing is you're going to be adding water to the grain mass, but that isn't always the case. And that's the tricky thing with natural air drying, is it's going to cycle. And sometimes you're going to be bringing in more moisture than energy, and you're going to actually be reducing or increasing the moisture content. But in the long run, you absolutely need that energy to reduce the to vaporize your water and to get the water out of your grain bin. But you can see by doing it with natural air, it is a huge benefit to have proper instrumentation on the bin, so you know when you're adding water to the bin and when you're actually removing water to the bin. It just, you know, there are a lot of complexities when you don't use supplemental heat, and it really is an inefficient way to do it unless you're very early in the season. With natural air drying, one of the very common, and I guess this is the current smart technologies that are associated with starting and stopping fans to allow you to dry your grain. They relate to your equilibrium moisture content, and ultimately that whole logic is basically saying that like if we take 60% humidity day, and if you say that you're running at 5 degrees, it says that your equilibrium moisture content is 14.6. So for wheat, that basically is where you want to be. And so then the logic would say, yep, let's run our fan and let's remove moisture. The problem with this logic is it doesn't take into account how big your bucket size is when you're running your fan at 5 degrees C. So you are potentially taking some moisture out, but you're taking it out at such a slow rate with these low temperatures that that is actually costing you significant money. And that's where having a real-time readout of what your cost per point per bushel is, whether you have supplemental heat, whether you have just your natural air drying, is a huge benefit, so that you know exactly what your economics are for the process. Now the third and the most common, I guess from our experience, the best scenario for repeatable and predictable in-bin drying is the use of supplemental heat. Again, you're warming the grain, but the difference is you are adding significant amount of BTUs with very little additional water. If you have a dry supplemental heating system, you're adding no water, but even if you are adding some water, the ratio is such that you always will be warming the grain, and so you will always have a big bucket. Oh, sorry, I went too far there. Here, you will always be warming grain, so the air will cool, and your grain mass will warm up, and you will very predictably add water. I'm getting lost here. Okay, you will very predictably have water removed, and the key there is that you're adding BTUs without any moisture, and that creates predictability. It creates a really dependable, reliable drying system. This mouse is acting up. So so that really kind of summarizes the bucket elevator. And here is just to kind of expand on that. With the bucket elevator, the big key is understanding how quickly your RPMs are. How many CFM should we be using? Pammy kindly let me use their interim research update data. So this is 1 year's data from their supplemental heating trials. And this is a plot of wheat, and we've got various moisture contents here. And it basically shows the rate that the wheat was drying versus days of drying. Now here's the first trial. They just used a very low rate of 0.25 CFM per bushel. You can see that the darker blue is the with supplemental heat, and the light blue is just with ambient air. And at that low rate, there really was very little drying. After 14 days, they actually increased the airflow rate up to 1.5 CFM per bushel, and you can see that instantly both the natural air drying in the light, and even more so the supplemental heating scenario instantly resulted in significant drying. I'll also add that the supplemental heat system they use is a delta T, so they add 10 degrees Celsius to the ambient. With our systems, I kind of like to just set my air temp at 30 degrees Celsius, and the reason, I guess, or the logic behind that is I see a 30-degree day as an ideal harvest day, and I just want to get as many BTUs in there as quickly as possible to get the job done. Here's a second trial at a half a CFM per bushel. This is the orange. Dark orange is with supplemental heat, and the light orange is ambient. And again, you can see that ultimately at the end of 19 days, we were down to about 16.5, and we started at about 17.5. And the last trial was 1 CFM per bushel. And again, it just is a step change of increased water removal with supplemental heat. This dark green line is significantly lower. The light green line isn't as aggressive, so you can see how the supplemental heat is helping. And now we're at about 14.5. So generally, very generally speaking, you double the airflow and you double the water removal rate. So airflow is critical. You also see here this 1 CFM per bushel, which is our guideline, and that guideline has really was generated from PAMI and from their recommendations. It is a really solid, I think, benchmark for when you are doing your in-bin drying. Here's some canola trials. One thing to point out on these trials is they did turn the supplemental heat off. You'll notice there's some strange anomalies here. They did that at about day 10. Here the half a CFM per bushel airflow. You can see the light blue and the dark blue is with supplemental heat. We went from about 13 down to just a little over 11, so we got about 2 points of removal with a half a CFM. We moved to 1 CFM and we got about twice that. We got about 4 points removal. And if you go to 2 CFM per bushel, you can see a super steep decline. And again, you double it again. So it really reconfirms that airflow, it's that simple. The more airflow, the more water you're going to take out of your bin. One interesting thing here to see is after they turned off the supplemental heat, you can see they were down as low as below 5. So this canola got quite a bit over dried, but it does re-wet by running the fan, and that is you know, and the re-wetting really is a function of how dry it is. The drier it is, the quicker it will re-wet. So that sort of summarizes the whole airflow component of things, and basically the functionality. The second component that we're going to look at is our aeration fans. Before I get into the actual aeration fan, I'd like to just discuss static pressure. It's a term that's commonly used, and it's something that it's really good to understand exactly what it's referring to, and the plain and simple is it's the discharge pressure on the fan. So it is basically what pressure that fan is pushing against. Here's some static gauges and static pressure gauges, and that's where you want to be installing them, just downstream of your fan and in the transition, so you know exactly what pressure that fan is pushing against. The units of measure for static pressure are inches of water, and that's something that's really hard to get your head around because it's hard to appreciate how small a pressure we're dealing with. Just to give you a bit of a feel, 1 inch of water is 0.0361 psi, so it takes 27.7 inches of water to make up 1 pound per square inch, which is super small. Here's just a bit of a to give you a bit of a feel for how small it is. This is just a normal balloon that I blew up, and I put a static pressure gauge on it, and you can see that reads 6 inches of water. So when we're dealing in inches of water, we're talking about the type of pressure that the human lung can put out, not the type of pressures that an air compressor can put out. Poorly engineered. When it comes to static pressure, the biggest cause for high static pressure are poorly engineered aeration system components. And this can, you know, again, it comes down to the fact that these aeration systems are just put in bins, and there's no attention to the technical design, and in many instances they're undersized. But it also includes putting too much grain in your bin. It adds lots of static pressure, back pressure, and having too small vents. Those items will be looked at in a future webinar, but that is what causes high static pressure. Now, for today's today's webinar is looking at how every fan has its own independent fan curve. So ultimately, all fans aren't created equal. They're all engineered for a specific purpose with a specific back pressure, and you really need to know if your fan is the right fan. And the way that you can figure that out is by finding out what kind of airflow it's giving for you during your drying events. Ultimately, you want to have, as we've said 100 times, you want 1 to 1.5 CFM per bushel is where you want to be, and you're going to get good, repeatable, efficient drying at those numbers. So I'm just going to walk through all the different types of fans and just discuss their sort of their merits. The fan mechanism for a low speed centrifugal is just your standard centrifugal water wheel type mechanism. It basically looks like this. The electric motor is on the back side here. So with these types of fans, you get no benefit from the heat from the fan, cooling the fan. Basically, all the air inlet comes independent. So you have a very slight loss of efficiency. It's relatively insignificant. These fans are designed to provide a high airflow against a low static pressure. Here's the fan curve plot. I've just got a standard airflow axis here, and we're maxing out at 16,000 CFM. I'll also mention that these are all the fans that I'm going to be looking at on this plot are 10 horse, and they're all grain guard fans. The curves, I just got them off the internet, off the grain guard site. But you can see here that at 7 inches of water, this curve has deadheaded. So that's the maximum amount of back pressure that this fan can see, and it is specifically designed for low back pressure applications. So that would be peas, corn, soybeans, and basically it can move lots of air when you have very low restriction. But even with that, you really need to have monitor your back pressure so that you know, because the danger with operating blind is that when you get close to this deadhead, your airflow drops off extreme. So you will literally get to no airflow if you are very much higher than this 7 inches of water. The axial fan is the second fan on the list. This is probably the most common fan. It was the original fan that was brought into agriculture. It has a unique airplane propeller look, so you can recognize it anytime you see an axial fan. The motor is right in the airstream, so it actually does conserve all the heat from the electric motor that the electric motor produces. It is again designed for high airflow against low static pressure. And here is a 10 horse curve. on that same plot. You can see it peaks out similarly, you know, a little bit less, but it deadheads at the same 7 inches of water column. But really what jumps out at you is you can see that at every data point on this, when you compare these two fans, the axial fan has lower performance than the low speed centrifugal. So it really, to me, it jumps out that there really isn't a lot of benefit to buying an axial fan. And I think the main reason so many axial fans are out there, number one, is they were the first on the market. So axial fans were very common. And secondly, is they're typically the lowest priced fan. But that's where buying based on horsepower is a huge mistake. You really have to look at these curves. You really have to understand your application. The next fan is an inline centrifugal. Again, the fan mechanism is the water wheel type centrifugal fan. It is an inline fan where the motor is in the airstream again. So again, we're conserving all the energy from both from compressing the air and the waste heat from the fan are being utilized. So it's basically 100% efficient. This design provides airflow against the higher static pressures. When I say higher, it peaks out around 12 inches of water column. So you do get a significant bump here, but you also see that that there's a significant reduction in the maximum airflow. So at 2 inches, you're only putting out not even 8,000 CFM, where the axial and the low speed are putting out 12 to 14,000 CFM. But ultimately, the inline centrifugal is a good fan for in-bin drying because it gives you a broader range of discharge pressures where it can move good air volumes. The high-speed centrifugal is probably one of the most popular fans in use. Fan mechanism is again the water wheel type. It has the look of some would say a snail look to it, and also some farmers refer to it as a Keo fan, and that's because Keo builds a fan that is a high-speed centrifugal. Again, this fan has the electric motor outside of the airflow stream, so you do lose the efficiency as far as not gaining that heat from the actual cooling of the fan. It is very a low amount of heat, but it is a small benefit. This fan is designed to provide airflow against high static pressures, similar to the inline centrifugal. Here I overlay a 10-horse high-speed centrifugal right below the inline centrifugal curve here. You can see, and what sort of jumps out is that the inline centrifugal is the better choice up until about 9 inches of water column. But then when you have a higher static pressures, you go up to the 11 inches, 12 inches, the high-speed centrifugal is able to move more air. And that's a big reason why I think the salespeople have in the past really pushed the high-speed centrifugal fan, and that really has become the kind of the standard or most popular fan in many instances on farms. And the reason for that is that it moves the most air against the highest static. So if you are filling your bins and you want to get as much airflow as possible, the high-speed centrifugal fan is your best option. But if you are actually filling your bins consciously and trying to get as much airflow as possible, I know with our operation we typically are in the 6 to 7 inches. So for us, inline centrifugal fan is the most efficient fan. The last fan, and this is sort of a premium fan, is the inline centrifugal turbo. The turbo has the similar water wheel mechanism. The difference here is that it has a slight taper to the body of the fan. So the inlet is slightly larger than the discharge, and with that, it's supposed to bring better performance. Whoops, jumped ahead again. Again, this fan is to provide airflow against a high static pressure. Here, because those fans, the turbos only come in a maximum 7 horse. So I've done a comparative plot here at 5 horse fans. This blue is our high-speed centrifugal 5 horse. Here is the inline centrifugal 5 horse. Again, slightly higher airflows at the 0 to about 7 inches, and then above 7 inches, the high-speed centrifugal gives you better airflow. And then here is your turbo fan, which based on the manufacturer's numbers, it shows that it gives better airflow on almost all points except at the very, very high static pressures. So, I mean, based on these numbers, it says that is the most efficient option. It comes at a higher price, and I certainly wouldn't say to go out and purchase, just turbo fans. I would really recommend that you get the instrumentation and you get your dashboard for your drying bins, and you see exactly where the best place to operate based on your aeration air delivery system, and see what your cost per point is. Find out how well is your system performing with the existing fans, and optimize with the existing fans. And at some point you might want to test a turbo, see if it justifies the cost. But again, you have to take manufacturer numbers are directionally correct, but I like to be able to actually use real data on farm to make your decisions. So back to static pressure. 7 inches was the deadhead for the axial, and the low speed, and 12 inches is the deadhead for the inline. So here's our 7 inches, and that is where essentially you will have no airflow when you're above 7 inches. And 12 inches for the high speed and the inline. Above that, you have no airflow, and it literally, these fans are designed that the airflow literally drops to nothing if you have too high of a static. Now, just to relate that to our balloon, if you look at the balloon, we've got 6 inches of water on this balloon. So ultimately, if you had a big enough balloon and you pull it over your inline centrifugal or your low speed centrifugal fan, that fan would have a very hard time blowing up this balloon. And that is how low these pressures are. So that just gives you a real good feel as to why the design of your air delivery system is critical. You have to have everything has to be engineered, everything has to be designed. Now, the last piece that I want to touch base on is I continue to harp about airflow, 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 understanding your fan. Now, the only real way to know your airflow and to understand your fan while you're filling a bin is to have an airflow gauge. This is something we developed a couple of years ago, and all it is overlaying a fan curve on a static pressure gauge. So here is your the fan curve for a 5 horse high speed centrifugal fan. This is the airflow gauge. You can see you're reading 2 inches of water column and 4,800. All it is that exact fan curve right on this gauge. So that at 6, it's 3530. And the beauty of this is then when you're filling your bin, you can gradually see exactly what your CFM per bushel is. You can calculate at every load. Now here is just an example of a bin filling event. This is using a turbo fan, a 3 horse turbo fan. It was a 2,700 bushel bin, and it's a T-Rocket with cross flow bin. So after one load, we had about 550 bushels in, and here we had about 1.5 inches of water. So you can see we were over 3,800, over 4,000 CFM per bushel. That works out to about CFM per bushel. So we've got huge airflow. We're going to add another load. You can see our inches of water bumped up to about 2.5 inches of water, and that is a little less than 3,800, so we're looking at 3,600 maybe CFM, and that's about 3.2 CFM per bushel with 2 loads. And again, very good airflow. Add another load, you can see you're up to just under 4 inches of water column here, and that works out to about 2 CFM per bushel. And then you add one more, now we're at about 4.5 inches of water. We're just under 3,400, so maybe we're at 3,200 or so CFM. With 2,100 bushels, that works out to about 1.5 CFM per bushel. So yeah, you can just see how this really is a valuable tool, not only for knowing your airflow, but more importantly, knowing if your fan is the right fan for you. In many instances, when you put these gauges on your low speed centrifugal fans, you really get an eye opener because they just can't push against the higher pressures. So that summarizes the presentation, and yeah, if there's any questions, I'd be happy to address them. Looks like we don't have any questions. So no, thanks very much for watching, and yeah, and ultimately, you know, we really want to be able to work with you. We want to provide that technical support to any in-bin questions. Feel free to contact us, and thanks for attending.